Alrighty, here we go. In this video, I'm going to talk about OpAmps and AC, and then we're going to talk about determining the effective or RMS value. So let's start with the OpAmps part. As I say anytime I talk about OpAmps, they are my very, very favorite devices in circuits and electronics. And so the great thing is that the steps apply exactly the same way as in DC, except we're using impedances instead of resistances. There are two very important things to recall. The first is that there is zero input current. I don't know why that's a theta. There's zero input current. And the second is that the differential input voltage is zero. In other words, if I have an op-amp, let's draw it with a minus and a plus, and this is V minus and this is V plus, then V plus equals to V minus, and the current IN equals to 0. Alright, with that stuff in mind, I would love to jump right into an example. So let's look at example number 1. In this example, I have a voltage source, which I'll call Vi of t. I've got a resistance R1, a capacitance which is 2 microfarad, going into an op-amp, minus plus. And then I've got a nice happy little resistor here. I'll call that one R2. I'll assign it a value here in a minute, and then a capacitance C2. These are connected to the output, which is V out, and then we're going to connect the plus terminal to ground. Alright, so C2, I guess I'd call that one C1 then. C2 is 1 microfarad, R2 is 10 kilo ohms, and R1 is going to be also 10 kilo ohms. And I want omega to be equal to 200 radians per second. And I want to find the input-output relationship between V0 phasor and VI phasor. Find the input-output relationship. VI phasor, which I'll call G phasor, or the gain. Okay, so what I want to do is this. I want to recognize that this is what I would call an inverting configuration, just like in DC. This looks inverting. So that means that V out over Vn, or the gain that I was looking for, is equal to negative feedback impedance over input impedance. So let's start by figuring out what the heck the feedback impedance is. It should be R2 in parallel with 1 over J omega C2, which is the same as R2 over 1 plus J omega R2 C2. You can do this math out, but you would find that this is exactly the case. And then Z input is R1 plus 1 over J omega C1, which could also be written as 1 plus J omega C1 over J omega C1. I've just combined these fractions together. Now, if I take G, which is just negative ZF over Zi, I should get negative j omega C1 R2 over 1 plus j omega R1 C1 multiplied by 1 plus j omega R2 C2. Plugging in numbers, G is negative J4 over 1 plus J4, 1 plus J2, and I calculate that out to get 0.434 angle 130.6 degrees. And this is a gain, so technically this would be volts per volt, if I'm getting my units correct. And that's the op-amp example I'm going to give. Now we can talk about the effective or RMS value. So let's start. The effective value of a periodic current is the equivalent DC current that delivers the same average power as the AC current. So if I care only about the power, what I can do is I can replace that AC current with something that's DC and figure out what the power actually transferred is. We don't actually know how to calculate average power yet, but we will get there. We need to start though by understanding what the effective or RMS value is. So we say the effective value is the root mean square or RMS value. We could say X effective is equal to X RMS, which is the square root of 1 over t integral from 0 to big T of x squared dt. So the square obviously is the square part of that. Taking the integral over the whole period is the mean, and the square root is pretty obviously the root part of that. Alright, so we're going to apply this here in a moment to an example, but I want to point out that for a sinusoid, in other words, Vm cosine omega t, then Vrms is equal to Vm over the square root of 2. So if it's a sinusoid, the RMS is just the peak value divided by the square root of 2. The same would apply for Im cosine omega t. I RMS is equal to Im over the square root of 2, which means that power is I squared RMS times R, or V squared RMS over R. Let's do an example of applying the root mean squared rules. So example 2, let's find the RMS value of the current waveform. And then if the current passes through a 2 ohm resistor, find the power absorbed. So here's my signal. I've got something that looks like this. Let's make that T. And this is 10 and negative 10. You would think I'd be better at drawing this with some graph paper, but I'm not. It's a periodic signal, which this is 2, 4, 6, and so on. So this is a periodic signal that repeats with a period of 4 seconds. So I'm going to state that here, T is 4 seconds, so that way you can see that. All right, let's solve this. So first thing we should do is define the function. I of t is defined as 5t for 0 less than t less than 2, and it's equal to negative 10 for 2 less than t less than 4. Alright, so that's the function of this signal. I got that by taking the equation of this line up here and then the equation of this part over here. That's where this came from. Nothing magical there. I just found the equation of that line. Y equals mx plus b. The y-intercept is 0, and so it's just the slope rise over run. So it's going 10, it's going up 10 over 2 time steps, so the slope is 5t. All right, so RMS is equal to the square root of 1 over t times the integral over from 0 to big T of I of t dt. So this is equal to the square root of 1 over 4 times, and then I've got to break this integral into 2 parts because I've got a function which is defined piecewise. I've got the section from 0 to 2 of 5t quantity squared, and make sure I get that back up in there. I've got 1 over t integral from 0 to t I of t squared dt. So 5t squared dt plus the integral from 2 to 4 of 10 dt. And that's 10 squared with a negative sign out there. So negative 10 squared. All right. So this is equal to the integral of 1/4, or sorry, the square root of 1/4 times 5 squared is 25, when I can pull that out front of the integral, times t cubed over 3 between 0 and 2, plus 100t between 2 and 4, which is equal to the square root of 1 over 4 times 200 over 3 plus 200. And when I take that square root, I get that RMS is 8.165 amps RMS, or ARMS. Hopefully, while you've been watching this, you've been doing your push-ups so you can get big old arms. All right. So the power here is going to be I squared RMS times R, which is equal to 8.165 quantity squared times 2, and that gives me 133.33 watts. And that's how we find RMS values. Remember, for a sinusoid, all I have to do is take the peak value divided by the square root of 2. These things will come more into play as we talk more about AC power in the future. All right, that's all. Thanks for watching.